In this example, we're asked to show that if two sets have the same cardinality, then there exists a bijection between those two sets. So first off, let's write this in logical terms. This is actually a conditional statement here. It maybe is not formed or structured as a conditional as we've seen them up to this point, but it is a conditional. So let's say this is our proposition P, that A and B have the same cardinality, and this is the proposition Q. There's a bijection between them. This statement can be read as if P, so if they have the same cardinality, then there is a bijection between the two sets. So if P, then Q. Well, the way I would like to approach this, and it's not necessarily the only way to do it, but the way I would like to approach this is by using the logical equivalence of the contrapositive. So the statement here that we're trying to justify or prove in some way, show that is true, is P implies Q, or P arrow Q. This is logically equivalent to not Q implies not P. Remember, this is called the contrapositive. This is the inverse of the converse, and these two are logically equivalent to one another, these two statements. So let's write this statement down. And this one says, I'll just write it as if then, because it's the easiest way to work with it, right? But if there is not a bijection between the two sets. So this is the negation of our proposition Q. If there is not a bijection between these sets A and B, so between sets A and B, then the negation of P is that the cardinalities are not the same, right? So the cardinality of A is not equal to the cardinality of B. So this, by the way, says that there does not exist any bijection. Not just that we have some function that's not a bijection. It says that no matter what function we have between these two sets, that function is not a bijection. Okay, so let's review some of these definitions here, and then we'll get on with trying to justify this or prove it, show it, whatever word you want to use here. First of all, recall that the cardinality of a set A, this is the number of elements or members of the set A, and we're told that the sets A and B have the same cardinality, but that this is very important here, that they're not infinite. So this then tells us that our cardinality is a member of the natural number set. So it's either 0, 1, 2, 3, etc. whole number, but it's not infinite. So it's one of these elements of n. And again, the assumption up here is that these are equal, but we're going to conclude that in our contrapositive argument that they're actually not equal. But this is called the cardinality, right? The cardinality of A. All right, well, what's a bijection? A bijection, remember, is a property of a function. Bijectiveness, or a bijective function, is a function that's both injective and surjective. And in terms of our calculus definitions that we've learned before coming into this class, injective means one-to-one, right? So this is just another way to say one-to-one. This means that for every element that's in the image of the function, there is exactly one element that corresponds to it in the domain of the function. Surjective, this means onto, and this tells us that the image is actually equal to the codomain. So the entire codomain is in the image of our function. All right, so let's think about this. We are saying, by the way, that our function is not bijective. So not bijective then comes in at least two cases. There's at least two ways to not be bijective. So not bijective could be either the following. So it could be injective, but not surjective. Right? It could be not injective, but still surjective. Or it could be neither of these two, right? So it could be neither injective nor surjective. So let's number these. Let's call these cases 1, 2, and 3. So these are three different cases of how we can be not bijective. And I'm going to justify these. Again, we haven't gone through formal proofs, writing formal proofs yet in this course. So I don't expect a formal proof on this one. But we need to justify it somehow using logical arguments. So let's go through these different cases and justify them, and I think the best way to do that is by drawing some kind of an image here. So let's go with case 1. So case 1, we say that our function is injective but not surjective. Right? So injective, not surjective. I'll just draw it like this, and I like to go with the blob and arrow method here. So here's our set A, here's our set B. If our function is injective, that means that for every point in the code, in the image at least, right? So the portion of the codomain which corresponds to the image, every point that lives there has exactly one arrow coming into it, right? And it's a function, so we know that the rules are obeyed for this f to be a function. All right, so there's the injective, that each of these have only one arrow coming into them. But the not surjective tells us what? Well, not surjective tells us that there's at least one point over here that does not have any arrows coming into it. Now, we know that the cardinality is finite. That's one assumption that we have to make for this this argument to work, right? But our cardinalities are finite. So in other words, this part we're still assuming that they're finite cardinalities. But for these to be finite, then what does that mean? Well, there must be at least one more point in B that's not in A, right? And so what do we conclude here? We can conclude that the cardinality of B must be greater than that of A. It has to be, otherwise this point wouldn't have anywhere to come from, right? The point is there because the function's not surjective. But the injectivity here tells us that, all right, the same number of points from A, right, all get covered here, but then there's one more point that's missing. All right, so in that case, by the way, that's a not equal. If the cardinality of B is bigger than A, then they're not equal. So for case 2, what are we going to say? Well, this time we've got not injective, but it is surjective. Okay, so not injective, but yes, surjective. Well, let's draw our blobs. All right, here's our A, here's our B. This time our function is surjective, so I guess I'll draw this in green this time. Surjective means that every point in the codomain B has at least one arrow coming into it, right? So these are covering, it's onto, right? So the onto kind of gives us an idea. But if it's not injective, then that means that there's at least one point. Let's say it's this one. All right, so every point has at least one arrow coming in over here in the codomain, but there is at least one point, if it's going to be not injective, there's at least one point that has two arrows coming in, right? So two arrows coming in. And in that case, what's that going to tell us? Well, this time that means that there's a point over here which does not have a unique output on the right-hand side. So the codomain is actually smaller in this case. So in this case, the codomain of B is less than, the cardinality, I should say, of the codomain is less than the cardinality of the domain A. All right, so in both of these cases, the cardinalities are not equal to each other. All right, well, the last choice here is that it's neither injective nor surjective. So it's neither one of these two. Not injective and not surjective. So let's draw our blobs. So there's our A. Here's our B. All right, well, we've done both of these together, right? We've kind of added these up here. So what can we say? Well, this one's a little bit trickier because actually there could be... so the problem is that it's not even possible to find a function that's a bijection between these. So remember, we're not dealing with actual functions here. So the problem with this statement of not injective and not surjective at the same time is that you could have a case where, just look at these two examples that we've done already. It could be possible that your cardinality of B, so you have one extra point here, right? But actually say there's one extra point over here as well, right? Which takes care of the cardinality issue by going here. All right. So the problem here is that this argument can't be done as pictorially, geometrically as the other two, because it's possible that the stuff that doesn't get covered with the onto could be the reason that the function fails to be injective, right? And so down here, if it's not possible for a bijection to exist at all, then what does that mean? Well, that means that this is kind of a heuristic argument. Again, we haven't gone through formal proofs yet, but it means that, okay, well, for it to be a function, every one of these points must have arrows going out, right? And so over here, if the image is only this much, right? Say this is the image, f of a. Well, the question is how many of these are double dips, right? So how many of these are extra? And if it's not even possible to define a bijection at all, then it means that there's either not enough points in this extra area that was missed, or there are too many points that it's not possible to cover it. All right, so actually the two illustrative examples are these two. I was trying to avoid getting too heuristic here. Heuristic means like just waving my hands, which of course in a video you can't see at all. But I wanted to have some concrete pictures here, and these two pictures, before I put this blue arrow here, so these two pictures tell the story of really the two reasons why this would not be possible, right? If we restrict ourselves to making sure that if possible we have an injection, if possible we have a surjection, but we can't get both, well then those two cardinalities are not equal. And then this is kind of just the case of, well, we didn't even try to get a bijection, right? We didn't even try. So the real issue here is that if you do your best to get an injection and you can't make it a surjection, then that means that your codomain has a larger cardinality. If you do your best and you make sure that you've got a surjection, but you can't make that be an injection, then that means that the domain itself has a higher cardinality or larger cardinality. Okay, and in either case, those two cardinalities are not equal to each other, and so we were going to claim that this justifies the contrapositive, all right, which actually gives us our result itself. That if the cardinalities are equal, then there is a bijection between them. At this point, you should stop watching the video, obviously it's going to end in a second, but you should think about a more direct argument that is a little more hand-wavy, a little more heuristic, but a direct argument of how to actually choose the assignment here, given, like, so you go through one by one through the elements of A and choose the assignment in terms of the members of B, and show that there's always going to be a possibility there to get exactly everything assigned to something else in the other set. Okay?